Okay, then if it's recorded, you can keep it brief. It's an offer. You take that, so it's good. Oh, it's good. 90 minutes. Next Tuesday, 1300. I think it's in this building, and the room is given in ISN1, so that's easy. So that's something you can check, but I think that will be okay. Calculator, a pen, nothing else. No notes, no formula. You don't need that. That's how it's made, so I'm not going to change that because it would change the whole story. So we have done it, and it works pretty well in this way. So that's for you and for me. So that's a good one. You have questions which you kind of prepared, or something that you would like to know? Anything that comes from your side where you are alone, or it's a bit unfair, so don't feel pressed. But if you want to understand anything, you can have a private lecture now. Which one?
Very complete, a lot of circles.
Okay, so you mean the Smith chart?
I really don't get it.
No, it's relax. It's nothing bad. Takes a bit in the beginning. This is the beginning. Very simple. Which, first thing is to understand why we do this. This is, when you get that, then it's very simple. Yeah? So the idea is, in RF, we have strange situations, which are, for example, that a cable is not connected. This thing, by definition, is open, which means it has the impedance infinity. Now, if you try to put that in a context which we normally would understand, so for example, we say we demonstrate an impedance of infinity, then to put that on a piece of paper is not very simple. And the reason why this is needed is that, and this is why this diagram is so useful, is that we want to understand something very simple. So if energy or a wave is traveling through that cable, what will happen here at this point? It's very simple, because if no energy is emitted, which typically is not, that's the only thing you have to understand here, the energy can be reflected, will be reflected and will be fully reflected. But this is also a bit strange, because what is happening if we short circuit the same thing? And then, for the same reason, nothing can come out, so if energy goes up, it is again reflected. So the question is, so something completely opposite, open and short, do the same, but there must be a difference, because these are completely different situations. Yeah? And this is why this chart is now useful, because you are for some reason you put the impedances, the resistances, you put them in a shape that you can represent infinity. And this is, so in impedance, this point is infinity. It's really infinity. It's not something like infinity, it's infinity. Yeah? And this is zero. This is zero impedance. So this represents zero. So you can put the opposites in the same diagram. And what is the distinction? And you take that from the idea of reflection. Now, if I have whatever impedance in what I am, so for example, let's assume this is a 50 ohm cable, yeah, and I'm leaving it open, then I know I will get a full reflection with a phase of 0. And if I'm shortening this, I will get a full reflection with a phase of 0. And the reason why I'm doing this, how do I know this, is that I'm superimposing Oh, there's somebody. Many people. Hi, we are back. So you can listen to the beginning. You can listen to the beginning because there's already we have already started asking some question. I was starting to explain the Smith chart again. It's on video, so there you missed about 3 minutes, but I'm just explaining why the Smith chart is actually doing something useful. Yeah? So the idea is that that you put two diagrams on top of each other. One is just explaining reflections, and the other one is relating them immediately to impedances. And this strange hacking there with the impedances, this is only done in order to put infinity to a circle. And why a circle? Because this is what a reflection diagram does. So in the center you have zero reflection, and then you have a magnitude. So this is what I'm showing here. Yeah. So there's a magnitude in this direction, and there's a phase. Yeah. And the only thing is just to visualize, you have some cable with some impedance, and you tell what is happening if you don't connect it, if you connect it with a short, or if you put any other impedances around. And the point is, for example, if I have a central impedance and I'm connecting it to something which maybe has now a real impedance, then I know I get some reflection. Yeah. So for example, this is 50 ohm and I'm connecting it to 100 ohms. Then I know there will be some reflection. Phase will still be zero. If I connect this to something which is capacitive, then I will know I will have also some reflection and magnitude, but I'm getting an additional phase term. Yeah, so there will be and it's not 0 or 180, but it's anything in between. Yeah.
So that exit is for the translate.
Now this is seen from the center, so this will be here. This is a polar diagram which has anything between 0, this is the radius, anything between 0 and 1. And the 0 diagram for I have to share it, sorry. So I'm not showing anything here. Sorry, guys. So again, the idea is that we are sharing, and now the radius of this diagram is between 0 and 1. No reflection would mean 0. Yeah. Some reflection, and then it has a phase term. Yeah. And why on earth do we discuss this? This is very simple, because you can connect the cable and you cannot connect it. And these are the two extremes. This is an unconnected cable, and this is a cable where you simply plug metal on top and connect the two poles. Yeah, so and they're doing the same in terms of reflection. You get always a full reflection, but you of course get it with a different phase term. Very simple. Yeah? And among those, and that is just the beginning, because it's just the beginning for letting you know that anything can happen, because we can also connect this cable to some impedance. And the next step is then to understand there can also be one thing which has any impedance connected to something which has any impedance. Now, how would that work? You would first think it from any impedance to this, and then any impedance to this. And you can also do directly. So that's also where the diagram is helpful. Yeah? But it's a help. It's putting some extreme cases, and that's, you can connect or not connect something to something real, and there can be all kinds. But the energy can only be reflected or transmitted, and that's both indicated here. Helpful? Any other questions that you would like to ask? So, for example, what if this is 50 ohms and this is 0 ohms? Where about is 10 ohms? Where would you say is 10 ohms? how would we find out? So here it's 50 ohms, and then typically it would have a scaling here. So there would be a node. Yeah, so typically I think 10 ohms would just be here. Yeah, so it's not necessarily linear, but there would be an additional marking. Yeah, so that's, but what is also typically given is, if it's a real diagram here, it's, let's check. I have one in here where the impedance are also marked. So the phases, as I recall, let me just, didn't do this nicely. I'll do it otherwise, just to wrap it up for everyone, to do it nicely. Smith chart with numbers. Let me just, I didn't exercise that. I can enlarge it if it's not clear. I reduced the contents not to confuse you, but I think this helps you now. And you can see here now this is the center line, and then these branches are giving you the impedance, but with I values. So let me just give you a better example. There's typically some which are, there are many versions of this thing, but some of them are confusing, others are helpful, and I'm just trying to wrap one up which is helping you in addition. So there's, for example, these branches then are this impedance, and then so when you are 50 ohms, you are on this circle. Yeah, so this circle is all the impedance which have 50 ohms as a real part. And if it's 10 ohms, it would be, for example, here. Yeah, and the question is now, and then there would be an annotation. For example, this would be 1 times I 50 ohms, or 2 times I 50 ohms, or 3 times and 4 times. So for example, if I have to build an impedance 50 plus 2 times I 50 ohms, or plus I 100 ohms, yeah? What I would do is I would just go up the circle till I meet this branch, and then I have the impedance 50 ohms plus 2 times I 50 ohms, 100 plus 100 I ohms, yeah? And this is the way it goes then. And then it's just the single scales on this tell you how much of the I it is individually, yeah? And the same as if you would build something capacitive. Why? So plus is always something inductive. Why is that? Because the impedance of an inductor is I omega L. It's a positive number by all means, which means that the top part of the Smith chart is inductive, and the impedance of a capacitor is 1 over omega C, and if you I omega C, and if you put that I up, then it's turning into a minus, so that means that anything below here is capacitive. So if you want to build something with a capacitive thing, you just say 50 ohms minus, and then you go down here and you, for example, hit here. I think this is, the reading can be done nicely. And then you see here, for example, and the 50 ohms, I think here this is 1 times 50 ohms. I was a bit early. So this is where you see the 1. Yeah. So, and this is, so for example, this is 50 ohms minus 1 times the reference impedance, and then it's, so then we are here with the 50 ohms minus I 50 ohms. And this is useful now for example, also for designing. For example, there's the conjugate complex condition. So where you want to have one network have the opposite of the other network in terms of the imaginary impedance. So for example, if you have one network has 50 ohm plus I 50 ohm, which would be here, this is the impedance to be matched. And then you just go to the opposite side of the Smith chart, and the other network has then to realize I minus I 50 ohm. So it's just a mirroring on this central axis. Yeah? So this is here, or this is what I have also in the charts. So here it's again what I just said. This is the reflection coefficient way of looking at this, and this is now creating impedances. So here you have, this is the reference impedance times 1, and then as I just did, this is the reference impedance minus I, the reference impedance. If the reference impedance is 1, then it's 1 ohm minus I ohm, 1 ohm, and if the reference impedance is 50 ohm, the same spot is 50 minus I 50 ohm. So this is a generalized thing. The only thing you have to give this thing, and you have to say, I'm doing this now in a 50 ohm system, or in a 100 ohm system, or in a 200 ohm system. The question would be, why on earth does he change the reference impedance? And that is very simple, because it helps you. Yeah? So for example, if we are looking at an impedance of 1 ohm in a 100 ohm system, then you simply don't see anything, because if this is 100 ohms for my reference, then 1 ohm is somewhere here, and I don't see anything. Yeah? Now I want to distinguish between half an ohm and 1 ohm, and on the page it's the same. Hope this makes sense. Yeah? So it's a graphical idea that you say, if we are going to a 1 ohm system, then I want to look at impedances in the range of 1 ohms. So because then it's easy to say 1 ohm is here and half an ohm is somewhere here, and then I can make a real graphical representation and see that, because then I can do something. Yeah? And why on earth would I do this in this lecture when we are forced to put out a lot of power? Then the impedances we look at will typically be very low. Yeah? And now you will get the task to put out 200 watts, for example, for a microwave base station, because you want to supply Freiburg. And then you are not interested to talk about impedances in the 100 ohms range. You are interested to talk about impedances in the half an ohm range. And you want to design there. You want to do these steps there. Yeah? So it's a matter of power. And then you select to look at your system with a low impedance system, and you just tell your program, we are now looking at in a 1 ohm environment, and then you get these nice graphical representations. Yeah? So because it's simply like enlarging. The only thing what you must not mix is you cannot look in one component in one reference impedance and the other components in the other. This will give chaos. Yeah? You have to look, when you're connecting components, you have to look at them from a reflection perspective in the same system. So you either do 50 ohms or 1 ohm or 10 ohm. Yeah? So this decision which reference impedance to choose is either given to you because you get everything in this system, or whether you do it yourself in a like kind of magnifying glass that you say, I want to look closer, so I'm switching to the other system. It's just a decision making, but not to confuse you. It's a practical approach, because if you're given a task to do something high power, then impedances will always be very low. Yeah? And what sets impedances, maybe just to say that very clearly, what is the impedance of vacuum? You remember that? That is it's a constant which is in the lecture script. It's 120 pi comes out, yeah, and this is about 377 ohms. So this is so nature gives us this number which is high, So why haven't you heard this number before? Because in practical terms, we typically go a bit lower. And that has to do with what I said with power, because impedances are always like, this is always simply calculated. So impedances is always voltage over current. And why does impedance go down when we are going to higher power? So in RF, the voltage at some points will be limited because we have to be small. Why do we have to be small for RF? Because only things which are small can be switched fast. So this typically limits this value. Yeah? So this is fixed. So if you then decide to put out more power, you have to increase I, because power, in the simple terms, and this is always right, is the product of the two. If this is fixed and you want to raise this, you have to raise this, which means that the impedance comes down. And why on earth do you need more power? That's very simple, because power means we are going over ranges. Now, why on earth can I not change this? Yeah, it is because you cannot change the weather. Because if you have to go from one point to another, the signal will be attenuated. And it depends critically how much power you start with, whether you can go from A to B, whether the person at the other end will get something or not. It's very simple. And whether it's raining, because the attenuation, what we get in the atmosphere, is determined by the physical conditions. And you cannot tell water not to be in the atmosphere, because you will build a system always on that under any circumstances you are able to reach person B. That sounds a bit strange, but it's useless if you have a cell phone system which only works when the sun is shining. That's not the requirement. The requirement is opposite. You say, whatever happens, whatever rain comes down, you want to reach person B with a minimum amount of signal, which means you have to bring a certain amount of power in, and then you are in this game here. These are simply constants of nature. Any further questions? The bipolar transistor, yeah, sure. The hetero-bipolar transistor, the founding of the which one is that? That's earlier, I think, sorry. I'm explaining it twice, that's why. So here or? So there's the two principles where there's a fundamental idea in this lecture which is based, what is current? Current is always carriers times good conditions where they can flow. Yeah? Now I'm trying to separate, because if I'm trying to get cars on the track, which is carriers, I will make the road bad. That is the fundamental idea, because anytime I'm putting carriers into a material, depending strongly on the temperature, but for where we are, it's relevant, this is a black line, then the capability of moving in this part of the device will be critically reduced by my doping. So I'm killing the path, because impurities in the crystal will kill the capability to conduct. That's essentially Ohm's law, because you want something which moves, and you have to get good conditions to do that, and you need the product. So you need carriers, and you need a good motorway. If the motorway is just good, no car, there's no traffic. We want traffic, so we need both. Yeah. Critical idea is now to separate that. Yeah. So what we do is we say we find a way to make a good path by making a material change in the material, which is essentially is a different band gap. So what I'm doing is I'm taking one material with a larger band gap on top of a material which has smaller band gap. The material with the smaller band gap will always be the faster one where I want the conduction. That's something which we also learned. Yeah, so smaller band gap means higher mobility. Yeah, so that's also clear. So I'm putting that on top, and if I do the right selection, then what will happen in the conduction band, the valence band will also follow, but in the conduction band, there's a large band edge and a small band gap. Yeah? So what will be needed is that they adjust somehow, because these conduction band, because it's then one crystal, they have to meet. And if I do this right, I will get a situation where this is the larger band gap material going up. There must be some difference to accommodate the overall difference. This is material dependent, but if you make a right selection, there will be some layoff here, and then you're going again to meet this band gap. Yeah. And the reason why this situation, which we are saying here, is interesting is that there's also this Fermi level, which is a very physical concept. But the idea is, the Fermi level is just this idea: how fast are the electrons which are able to move? Can they fill up in the energy band? Yeah? And typically, when the semiconductors are undoped, they're somewhere in the center, and they are also the guiding principle for the adjustment. So they have to be equal on both sides, because there can only be one level of water in the crystal, so to say. So this is where the electrons are. So you see, because they have to be equal, here, this bending occurs. And now something happens, and this is designed, that this band-off energy, this offset energy, crosses the Fermi level. So this goes under the Fermi level. This is good, because band gap under the Fermi level means that the carriers are in the in the range where the electrons can conduct. They are in the conduction band, and this is where they can move. Yeah? So what have I reached here? I have reached a situation that very close to this interface, the electrons want to be. So here in this part. And they stick there very close to the surface. This only works because we are so close. It's only working in the quantum domain, so it's not working for large distances. It's only working because we are very close to that, because there will be strong changes here in the change. And so what you get by this is that you have suddenly, before the electrons could be wherever, and now they are next to this interface. And this is perfectly attractive if you do the things right and everything is good. So for example, the interface is smooth. Then you have created something which inhibits the electrons to go anywhere, and it's like a pipe, or it's a 2D pipe. So you have a flat layer of carriers which you only have to interrupt now. So this is something which you can do. Then you have them in a defined state, and now you can put a contact on top of that with a device, and can interrupt them in a very defined way. This is what. So it's like before, if you have a large pot of water, that's hard to control. But if you have it in a tube, And this is exactly what's happening here. If you have it in a tube, you can put a shutter and interrupt the flow of the carriers through the tube, on, off. Yeah. So you have a, and what did you gain? You gained very good conditions. Why are the conditions good? Because we will not be doping this material, because this has still the nearly ideal conditions for moving. Yeah? We will dope the other side of the interface, this one. And why on earth will then, so the donors will be on the side of the material, and we are not really in problems because they deteriorate something there, because for energy reasons they will want to get away from their donors, the electrons, and want to go here. What is new, and this is now the quantum part of it, why should something, if this is the energy axis, why should they go from here to here? Because there's something there's a barrier in between. But then you remember something which you heard about quantum physics before. If it's close enough, then electrons can tunnel, and they don't see a barrier. If we are getting into the thickness where the quantum laws apply, then the electrons can tunnel into here without any energy. They can just go. And that's good, because then suddenly they want to be here and gain some energy also, because they're here in this quantum pot, as we say, and then or quantum well. So what you get now carriers on the nearly ideal motorway, and you can also cut the motorway. That's because you have reduced the dimensions. Yeah? So without having to made a device yet, you have a fine plane of electrons near a defined interface, and the properties of this material are nearly ideal. They are better than, so what you win is, if you had doped this part, if you just doped one semiconductor, you would be here. But if you are not, you don't have to dope them, so you don't kill the mobility, you get much higher mobility, but and you can put a lot of carriers, because the doping which you do in this regime here is independent. You can put as much as you want. So you can, it's completely independent, and then you will have high number of cars on a very good motorway, and the product makes much better current. Yeah? Question is, why would you do that? Because this property will be linked directly to the gain of the transistor. If you get this up, the ability to amplify is the product again. Yeah? So you want this number to be high. And it's directly proportional also to gain, and by that also to efficiency. The higher you get the current, the higher you get the voltage capability, the higher the power, and it's going to be, because you have high gain, it's going to be efficient. And with these devices, you can address frequencies which you otherwise cannot address or cannot effectively address. That's the main reason why we do this. Yeah? So there's a reason why you want that. You can say all this stuff is not needed, but you have a requirement because you don't want to consume the power in your network when you use this. Yeah? And you just want to. Okay, any others from the audience? Anything from the room? Anybody wants to ask a question? I don't see anything in the chat. Anybody wants to speak up or just ask a question? I'm referring to you to some of these questions which I already asked last time. So maybe had some of them already, so we tackled them already. The free space impedance, this is this 120 ohms, yeah. Let's see whether I can free space. We went through this, and what we came out with, this was this, maybe this helps you also for the Klausur. The idea was, it's very tough to understand why there's energy transported, but you know that there's a vector, and there's an E field and a B field. This is something which I think you understood before. And the trick is that this unit of this cross product, this vector, we call that the pointing vector, it's E cross H. Yeah? And you can say, oh, what a strange concept. But there's one thing which you clearly can understand without any hesitation. It has the unit of power per area, watt per square meter. And why is that? The unit of the E field is volt per meter. The unit of the H field is amps per meter, which is very helpful. The product of volt and amp is power, it's watts. Yeah? So it's energy per time per meter, which tells you that something is moving in this direction, because you also got this direction with the cross product. So E times H is a vector which has the unit of power per area. So there's power transported. And if power is transported, there's also information transported. Very simple. You don't need all this physics. It's very simple. You just take it from the unit, and it's fine. Yeah. And the other thing is what you asked earlier. Why is impedance related? Is because if you take the ratio of E and H for the moment, why would you do that? Then you're coming to something which has the unit of ohms, because you're dividing volts per meter by amps per meter, which the per meter cancels out, so it's volts per amp, which is ohms. Yeah? So you're defining an impedance as a function of the material parameters. And which are those? If you do that for anything, it is the magnetic constants by the electric constants. Yeah? If you are in vacuum, you can scratch out the square root, and then you get the ratio of the mu0 by epsilon 0, which are high numbers you normally don't regard, but they are 120 pi. And this is a fundamental constant in our life. If you go to space where there's nothing, total vacuum, it has an impedance of 120 pi. That's true for everyone in this universe. Very simple. And that sets a unit of an impedance of 377 ohms. So very, very simple. No physics at all, just a little bit of knowing of simple wave traffic. Anything else? So that was the pointing principle. And then there was some things. So for example, if you we did this before, but if you put 100 ohms plus I50 ohms in the Smith chart, center is 50 ohms, you go a bit to the right, and then plus is the top. You just check where's 1 times the reference unit, and you're there. And if you do the conjugate complex of this, you just mirror. So it's very simple. Yeah? The HAMD faster than the MASFET, this is what we just said. You have more carriers on a better motorway if you separate carriers from doping. That's what I just explained earlier. Yeah? And the bipolar transistor, this is the other setting, so let's go there. Why is the bipolar so precious? Why do we want to talk about this. So the early idea was you put both carriers, electrons and holes, in a device, and you see here what is the issue. You have to keep the emitter concentrations high to get a very low resistance, and then if you need a P base, which you also want to dope as high as you can. But if you do that, the trouble is you get this fish tank effect, which normally helps you. But in this case, it's a bit counterproductive because the electrons should go into the range of the base. But if you put too much base doping, then the base will also, the holes from the base will also want to go back. Yeah. And what we are trying to do here is we want to send as much carriers in the positive direction that they go from the emitter to the collector. But we have to make sure that the control current, the one which controls us, is low. Yeah? If we now have a high concentration of base holes, then this current will also go up. But that's stupid because the ratio of the controlled current by the control current is getting worse. And then we use this principle again here, that instead of just putting one material and dope it, we put again a high bandgap, low bandgap combination. And this is good because now here, this is the situation which we explained earlier. So the electrons can still travel because they can tunnel. That's no problem. They can go in there. But in the energy scale, this is now important. When a hole is energized, it goes down. Yeah? So that means this additional barrier, which is formed by this wide band gap in the emitter, in this case, this is serving as a barrier. So this current will not, repeat not, even if we dope very high the P base, the current which we control, which we use as control current, will not go back into the emitter. So the ratio of what I'm controlling and what I need to control is getting better without me, and relatively I can put much more base doping into this. And why would I do this? This is explained here. I want to dope this part as high as I can because I need to connect the current through something. So the resistance to send the current in there needs to be really low. The resistance has to be really low. Yeah? So I will put everything I can in this layer so that, but I don't want the holes to go back here because this would kill my current in the plot. This is this plot. And what do I plot here? Just to remind everyone, this is also a very useful finding. I'm plotting here the two currents as the function of the input voltage. Yeah, so this is the current which I'm using, and this is on a log scale. So there's an exponential difference between the two. Yeah, so this is not just linear. So this current which I'm controlling, is orders of magnitude higher than the other one. Yeah, so if I can use a very low current to control this current, it's better. So if I was plotting a bipolar transistor without this hetero barrier, then I would get this. If I'm getting a hetero barrier in there, that will be much lower. Yeah? And the ratio is my current amplification. So it's how much current I need to get, how much current out. And I want this, of course, to be very high. Yeah? And the reason why we make use of that is very clear. Because getting higher current gain would consume area, and I'm just gaining an advantage also in size to control the same current with a much smaller device. That's why I'm doing this. Yeah? So it's and when you want to have this in real numbers, in your real experience, yeah, if I'm having an advantage in this structure, Your cell phone won the heterojunction bipolar transistor won the Nobel Prize because it does something at the lowest area, because it has this junction in there and it has the hetero barrier in there. And if it does that, then I gain a size advantage, because I can get the best value, so I need the size of my cell phone. If I do it with another transistor, just a bipolar, the cell phone will be bigger, doesn't fit into my pocket anymore. And if I'm comparing it, for example, the same feature with a FET, it still can be done, but then my cell phone in area needs the size of my laptop. So you see there's a real advantage in having this relative advantage. Yeah, there's really, this is not just some currents which we say, it is how much current amplification I can get per area. Yeah, and this is the advantage of heterostructures, because I can put more doping, otherwise I would have to restrain myself. Yeah, this is this Gummel plot. It's not a Gummel plot, not German. It's not the German word. It's a name, and because the first person to plot this at Gallups was Hermann Gummel. He plotted that and he saw that this was useful. Okay. Any other question? And here you see also, maybe this is interesting, you see the impact of the parasitics. So here we have such a transistor, and you see the transistor is very small, but we also have the surroundings, and you see they are very large. And all the metals are very broad to have very low resistance, very good conductivity. So we take copper to get the best connection. And at the same time, we use the 3D effect here, because the base is contacted to the top, the emitter is contacted to the left, and the collector is contacted to the right. And in this way, we make sure that the overlap of the metals, which have to be large at one hand to get the conductivity up and to make them very low resistance, but at the same time, we have to avoid capacitances. Yeah, so you see that the collector, so this collector is only overlapping with this part because this goes to the back. Yeah, so it's only overlapping for this small area. If it was in parallel, they would build extremely high additional capacitors, which would reduce our speed or our gain. Yeah, that's not good. Any other questions? Still have 10 minutes if you want. If I explain it, you don't have to learn it. So is there anybody else who wants to know something? Any update on the chat? Can you guide about the exam pattern? The exam is a written exam. You bring a pocket calculator, 90 minutes, a pen, and no notes. Yeah, and the idea will be answering this type of questions. There will be also some short calculations that will be relatively minor. Yeah? So this will not be. So these will be questions like that. And there may be some short exercises like putting, for example, an impedance into a Smith chart, or maybe some very simple equations are in there. For example, for the cutoff frequency, for example, this is essentially transconductance over capacitance, input capacitance. This is just, so there are very few equations in the script, so there's no need for formula connection, but there's very small ones. So what does make, for example, the cutoff frequency? And then, for example, this is, for example, here, for example, these are fundamentals. So this is the max gain is GM over 1 over GDS or RDS. So that means that amplification can only be the product of the two. So it's not only the transconductance forward, but there needs also to be in resistance included, which has to be high. Yeah? because only if the resistance is high, the max gain will be high. And then here the cutoff frequency and the current gain is approximated again by the same idea, transconductance as high as possible. But there's also a capacitor to load which reduces. This is mainly the in-code capacitance and a little bit of feedback. So this is something which might help you. And what is the contradiction in this? Because if you there's also some understanding here for the FET. No, not this way, the other way around. Here, these are these plots. So a few equations. The current in a FET is proportional to the square of the voltage, of the input voltage. In a bipolar, it's exponential, as we just saw. And there's one contradiction. You don't need to learn this formula, but there's one idea which you have to, that these equations are identical. Yeah? So if you increase the transconductance, how can you do that? There's only one way. You can select the right materials, so you have a good effective carrier velocity. And there's an effective distance. So if you can control the current better if you make the distance between the gate contact and the channel shorter. In CMOS, we call that the oxide thickness. So you make it thinner, not only in the size, but also you make the whole thing thinner. You need that to control the current. At the same time, from the simple equation of a capacitor, so this is a simple capacitor equation, you can dF and HF are roughly the same. Yeah? So you see that by reducing the distance of the carriers to the contact, you also increase the capacitance, which means that you are not winning anything in the ratio of GM over CGS. So there's no winning of speeding up. The only way how you can make a transistor faster is to reduce its gate length, which is LG, which is the length of the gate contact. This is why small transistors, especially in the gate length, what is the gate length, which is this length here, from here to here, or in a CMOS, the same. So there's a contact, and you make the gate contact small. And that's why we need this lithography, which we talked about. That's the only way for any FET how you can make the device really faster. Yeah? And in opposite, that's also why people made memory small, to have as many memories as possible on a given area. So they made all the dimension of this small, including also the gate length. They made the transistors very small in area. This is the width, but that is not the only thing. They also made the length small between the contacts, yeah? Which means that by reducing the speed to represent the bit, they also made the switching very fast. That is not the original intention, but they simply, because they reduced the area, they were reducing the capacitors very clearly. Yeah, so you're reducing this capacitance, which is the speed relevant capacitance of the device. Yeah, so that means that by just making good memories and many bits per area to put it into your pocket, you also win something which is extremely fast. So that's why the CMOS memory chips are also very good RF transistors. They have one problem, which is the smallness, and this is something why we need also other semiconductors. This is here. That's, you can see here. Whenever we make something too small, then we lose one thing, which is which is why I have this thing here. If you put the distance between two contacts too small, then you will accelerate the electrons in the channel too much, and they will start to kick out electrons from the crystal. And that's problematic, because if you make the voltage too small, then we are again at the beginning of the lecture, what we just discussed with here. If we want to have amplification, we want current and voltage. So if now we can get current switched fast, that's good. But if the voltage reduces too much, you can say, okay, I accept that. But there's two problems. First of all, if the voltage gets too low, you have voltage too low times current goes up, okay, but the power will be limited. Yeah? And the second problem with this is that if the voltage gets too low and the current goes up, again the impedance goes too much down. And that's the same problem which we discussed before, which we started with. Yeah? Okay. Any others? We put an hour, so again, meet you next Tuesday, I think at 1 o'clock. Room is given in HISM 1. No notes, a scientific calculator without programmable functions, a pen. You in good mood, you have 90 minutes. The exam will not be too stressful in terms of time. You have time to think, write things down, check what is really asked for. And one thing I recommend, if you, for example, learn something, take a pen before and write it down. Not just learn it, because when I think I have understood everything, trying to write it down, I miss 50% of what I think I know. That's my problem. Maybe you have the same problem, so take a piece of paper, take your electronic pen, and just reproduce what you learned, writing it down. It's helpful in the exam, because it should happen before you do it, and not in the exam. If you're sitting in the exam, oh, I missed that, that's not good. If you just write it down, you can check it, and okay, this plot has this unit. Yeah? Don't be afraid of this Smith chart. It's very simple. It is a great help. Just play with it. There's also some tutorials on it. It's very relatively nicely done. I think within half an hour you can completely familiarize it with it. It's not, and it's a help, because you can say it's a crazy diagram. Yes, fully right. But it's a crazy diagram which has infinity. And infinity in a Cartesian diagram is out of the room, so maybe not so available. I hope that helps you. And okay, this is recorded. I've recorded this, so you can listen to what I just said again. See you next week then. Happy learning. Prepare yourself. I like that. And I'll see you next week then. Thank you very much.